this morning we discussed the field extension defined by mapping, holomorphic mapping in a one-dimensional case. Of course, we assume x's and y are compact and connected, and that the map is non-constant, so it's really a ramified cover. And we observed, if you, let me draw the usual picture, say, just to make a reminder of something like this, that if you have a function upstairs, say at good points, above a non-ramified point, so here where it's 4 to 1 really, it may have 4 values, value 1, value 2, I'm writing German, so you should be happy. Value 1, no, that'd be a vector, so I'll stay with W. W1, W2, W3, these are the values of the function. And of course, it doesn't make sense to talk the first value, second value, third value, there's no such thing. They're just 4 different values, so what you associate to this is a polynomial in one variable. In the general case, various values over this function. And these, of course, are varying holomorphically. If you vary here, that varies holomorphically here. So this is really a local holomorphic function. And if it's a k to 1 covering, then in general you have k values. Of course, you will have degeneracy, but you have to worry about that. It's not much of a problem. You just analytically continue here. And this is a polynomial degree k with various coefficients. Maybe we write them here. Sigma 1 k minus 1. The sigma 1 is the first elementary symmetric polynomial in these things, namely the sum, and the sum of products, second elementary polynomial, and so on. Will look like this, and these functions, since they're symmetric functions, do not depend on this order, so that these things are in fact, let's say sigma 1 through sigma, how many do we have maybe here? Okay, and our meromorphic functions on the base. So the base was y. This morning I introduced this notation, just round bracket as the meromorphic function. So let me just say I will use notation. So that says every function is algebraic. Upstairs is algebraic over the function field of the base. And the algebraic of degree k and most, where k is the degree of this map. So that's the statement then that follows just by elementary algebra, that upstairs is the same as downstairs, except you have to add some algebraic extension to a certain degree bounded by, well, whatever it is. So that's a discussion of the one-dimensional case. Then we discussed an example in a two-dimensional case. This is looks like a simple-minded example, so let me write it in naive notation. M of ZW, so on the manifold, which is the easiest of all manifolds to understand, C2, And this thing should be z divided by w. And then I talked about how this thing looks in the neighborhood of the origin, where you're worried about what it means. So on the z-axis here, z means w equals to 0, so you think along the z-axis it should have the value infinity, and that's really the way to think about it. So around here, along this axis, where w equals 0 here, the function should somehow be identically 0. And then maybe use another color to emphasize that.
It's infinity, yes.
Oh, did I write 0 again? I'm sorry, yeah, m should be identically 0. Infinity. And here, the other way around, so this thing is where z equals 0. And of course, then the top part is 0, and that's not, so the function here should be identically 0. And then I just pointed out that if you take any line here, say this line here, so this is a line, as you know, a one-dimensional subspace. So a one-dimensional subspace is parameterized by a point in P1, and then the value along here, I don't know.
How do you define it in 0?
Hmm?
How do you define it in 0?
Well, I'm just going to tell you. You didn't object when I said it should be identically 0, infinity here, identically 0 here. And then I'm going to tell you here it should be identically whatever it is. I mean, this is the line defined by that, so let me just say what that means. That means this is a point here. Let me use this. Z0, Z1. So these are all the factors of Z0, Z1. So I guess this line here should be Z0 divided by Z1, I hope. Right? So this is Z0 equals the lambda Z0, Z1. That means Z over W equals lambda times Z, I don't know. Oh, no, I'm sorry. Equals that, and that equals Z0 over Z1, and that's lambda in this previous notation. The slope of the line. Okay? So on here, I'm going to define it as Z. See, this is somehow the slope.
It's 1 over lambda.
Is it 1 over lambda?
Yeah.
Maybe. Well, I don't know why. Is it, I see. You're right. It's probably 1 over lambda. Okay. So, as the line changes, the limiting value changes, so of course it's not defined at the origin. At this stage of the game. We went through this this morning. Let me just sketch it again. So, the setup here is the indeterminacy set of the meromorphic function, called the indeterminacy set. In this case, will be just one point. So in general, as we said this morning, a meromorphic function is given on, say, localization, where we have it as a ratio, as a quotient f divided by g, locally. So this is a local representation. And we can always organize it so that these things are relatively prime at every point in U alpha. They don't have any common factors. You can always organize that, and what that means is that, for example, dimension 2, f will have a certain zero set, maybe not irreducible, I draw it like it's irreducible, and G also, but they don't have any common components. They intersect but no common components, that's what that means. And then the indeterminacy set will be locally well defined, it'll be globally well defined, and it's locally just where both things are zero. Right? And that's really a non-trivial condition because there's no overlapping of the one-dimensional components in dimension 2. So this is a codimension 2 space. In this case, it's just isolated points. Well, that's the story. Meromorphic function in higher dimensions is not well defined, not necessarily defined a priori. Everywhere it has indeterminacy. Yeah.
What do you do when F alpha and G alpha are both infinity at the same time? What do you do when...
They're holomorphic. Okay, by definition.
So they cannot be...
No, it's a ratio of two holomorphic functions, locally. Okay?
Well,
Yeah?
How did we get that it's codimension 2?
Again, yeah, I made a big discussion of that this morning. You might take a look at the video, but let me just roughly say what the point is, okay? You're absolutely right. What could happen, let's, here I drew it, here, let's say this is F alpha equals 0, and this is G alpha equals 0.
By identity principle.
Hmm?
By identity principle. If they're the same on any line, then they have an accumulation point for their...
I understand what you're saying. They could be the same on some component. That's what you're saying. So, and you see what may happen here is this thing may have a multiplicity of 8 and this one has some multiplicity 25. So what's important to say, you have to allow multiplicities along these components. And then you begin to understand what's happening. So what could really happen is what I discussed this morning is a priori, this part could be a component of, say, as an example, of F alpha of multiplicity, let's say 29, but it could be also a component of G alpha of multiplicity 18, as an example, who knows? And what we talked about this morning, what you do then, and this is because the local ring is a unique factorization ring, you just cancel. So you cancel out in this ratio, and then G no longer will have a 0, and what you get here is F will have a 0 order of 11, okay? But you have to prove you can do all that, and that takes quite a bit of understanding of the local, so-called local algebra.
Hilbert theorem, there is Hilbert theorem, no still is that?
Say it again, please.
Hilbert theorem.
No.
It doesn't have?
No, you need to really understand really the way the local ring looks, and this means you need to understand locally the way a function looks, and this, for that you argue with so-called Weierstrass preparation theorem. Let me just tell you what that theorem says. It says, remember one variable, after normalization, f of z equals z to some number, holomorphic function. And this theorem is certainly not true in higher dimensions, but what is true, and I'll tell you why it's true, you will enjoy the proof, you will prove it yourself. Of course, I've normalized a constant way here and say, I'll say in two variables, just, that's all Weierstrass cared about at first, maybe. I'll make some normalization so I won't bother you. I'll draw a picture of what happens. Let's say we're analyzing the function in the neighborhood of 0, and this is the z-axis, and this is the w-axis, and this function has a 0 set. Of course, I have to take these axes in good position with respect to the 0 set, so what I'm saying is after taking a good position, and what happens is, it's the same old picture. It's the same old picture. It looks like this. The locally speaking, this is a lie. This may not be reducible like this, but it's a 2-to-1. It's 2-to-1 locally there. So what happens is, in the zero set, well, so if we cut it, so we make a little box here, so that locally it's looking something like that. And now, so I'm going to draw it here. This is no proof, but I want you to get a feeling for what's true. This is proof of Weierstrass theorem. So here's what it looks like locally, if you make a projection. So this is projection on z, so if you have some value z, a fixed value of z, you get this thing has 2 zeros. So for a fixed value of z, this is a polynomial with 2 zeros. And so what's a polynomial with 2 zeros? It's a square, so it's w squared Latif. You can tell your students here about this polynomial degree 2 and they can solve it. It's w squared plus some constant, a1 w, I don't know. Everybody agrees this is a polynomial in w, right, with 2 zeros, right? And now what happens is, that's for a fixed value. So these things, it's very close to what I've just been discussing. These coefficients vary with z. And of course, that's if I allow myself to have this leading coefficient equal to 1. Actually, to be precise, the leading coefficient should be a unit in the local ring of functions. So, I mean, it's just something that doesn't vanish. So the point is, you should think of the zero set as being understood when these things, when your fiber here moves, and as your fiber moves, you have a polynomial of degree 2 which is moving. Suddenly it might collapse here to singularities, but that's over a small set, and that's the way things look. This is so-called Weierstrass preparation theorem. Easy to prove. The proof is just what I said here. How the number of zeros, you know this, it is so-called Rouchet theorem that says as you move, the number of zeros doesn't change, the polynomial will change. But the number of zeros will not change, counting multiplicity. And that's what's happening here. As you move, you have 2 zeros always, but the location of the zeros clearly changes. And you see, this is inside of a disk. Here, each thing is a disk, so Rouchet's theorem is applicable. Remember, if you have a function, you move these zeros through the boundary of the disk, Rouchet's theorem is proved by an integral, and that makes a singularity where you've been integrating, and then suddenly Rouchet's theorem is false. The number of zeros changes if you move something through the boundary. But you see, this is all inside of a disk, and that's actually a detailed proof of what really happened. So I don't know why on earth I said that. Oh, so I said that because you asked me about the setup here, and the thing is, then it's not just some thing, but locally speaking, it's very, very good. And then in terms of these Weierstrass polynomials, you can understand very well the local algebra. So what we're talking about locally at a point, how a holomorphic function works, okay? So Weierstrass preparation theorem. And that allows us to do all sorts of things, like, for example, prove that local ring is a unique factorization domain, so you can cancel out stuff. Okay? It's important. And then once you cancel out, no two components agree, that means they may intersect, but they're both one-dimensional, so they intersect in 0 dimension. And that's codimension 2 that we're getting, okay? I don't hope you're happy with that. Okay, so that's a bit of a review about this morning, and I think it's nice that we can review the morning, not just because a couple people weren't here, but it's good to think about. Okay, and then now this other point point is that, let me just get back, I cancel everything, but still we have this bad isolated point. So we, in some sense, redefine now the notion of meromorphic function or map. And I'm going to repeat this because this is fundamental historical remark. So in old days, before the Second World War, there were German mathematicians, for example, here's the name of one, named Tin, who was interested in meromorphic maps, and his definition of a meromorphic map is locally given by k meromorphic functions. Right? I mean, you see what I mean? That's the way you define a holomorphic map. It's locally given by so and so many holomorphic functions. This, in some sense, is okay, but it's not good. So the good development is after the war two people in my mind who really understood the point. Rembrandt Stein in Germany, in Münster, understood the notion of what should be a meromorphic map. I will simplify it a bit here. See, I just have some example there. I'm going to study the example more thoroughly in a minute, but just let's get a definition. And what they understood is, the key thing is that the value of a point, of M, so say of a mapping, which I'm going to write like this, it's not everywhere defined, at a point is a set. So the correct notion of mapping here is it's a set valued map. And you see what's going to, well, like in our example, so the meromorphic function of a point, oh well, I just wrote up a point, say the value of the point z 1, 0, that's of course 0. And the meromorphic function of the point, say 8, 0 is infinity. I don't mind infinity, but the value, well, maybe you should, let's be careful, it's a 1 point set. But the value at 0, this is a fundamental breakthrough philosophically to get through this thing. The value of 0 is P1. See? Because it takes on every value. It takes on every slope. On every line. So the value is really P1. You just have to accept that. Now, that's just some blah blah, so now let's be precise. Rembrandt's definition, coming also from Stein, of a meromorphic map.
So don't you need to have isolated points that...
I'm talking about in our example, yeah? What do you mean isolated point?
I mean, anything, like any function on this world has the value like a set, but you need to have special
Any point
values.
it's a set value map. So given a point, you evaluate, you get a set.
It's that general. It doesn't have to be continuous locally. Or
No, you're right. From now, this is, you're right. I mean, this is nothing. Yeah, but I'm not finished.
Okay.
Yeah, because it's not going to be continuous, right? We agree with this, but, okay? So, So, the way to do this precisely, I'm now going to give you Rembrandt's definition. And by the way, this was made precise in the early mid-1950s, so this is not so long ago.
So I also have a question. If, according to your definition, should f be mapped from x to the power set of 1?
Absolutely. Absolutely. So, that's right. The set value map is a set contained in, yeah. Okay, just exactly what, I don't know your notation, to the power set of 1. Yeah? Yeah, some set. I mean, this is what Mihai is saying, this is ridiculous, I mean, just as a general definition, but we need more. Okay? What in Shinta, what's the point?
Because your set is, the value of the map at a point is a set, then this map shouldn't be from x to y, but to x to power.
You're absolutely right, but we write it this way. And
But then the topology of the y will also change, then we cannot say that.
you're making a very good remark. So the first thing is notation. Just keep in mind, and you can, this is even in tech, that I use this notation of a half arrow, and this half arrow tells you that you're right. It's not really defined, it's only really defined as a map into the power set. Okay, but it's much more than that. So we were talking this morning about my granddaughter who's 11 years old. Of course, what happens here is you have a graph. And you have a graph of this thing, and usually, so the graph of f we will denote by the graph f. And so far I didn't say anything, but you know, by the way, I don't know if you ever thought about logic, but a function or a mapping has to be defined as a graph, right? I mean, that's one of the first things, it's a subset of the power, right? And now, of course, usually in elementary mathematics, you take a point here, and in the 5th grade that you learn, this is f, maybe you don't learn, this is f, x, f of x, right? And then you think that this graph is a graph y equals f of x, right? Okay, that's what you did in the 8th grade. But now we're in the 9th grade, and y is a set. So over x you have a set. Now we're still in, your objection is completely right, and Mihai's objection, everybody's objection is right. However, we have the following situation, and now comes Remit's definition. So we have the graph of this thing is a set. We're going to say the meromorphic function is a graph. We're going to write this arrow down here because it's not really defined yet. So this is a set, and now we go. This is an analytic subset. So that set, you have to be careful what that means, but it's just i.e. locally defined by holomorphic functions. So this is an analytic subset in x cross y. Okay. Right. With some reasonable properties, not just something. So if this map is f, I think Stein's notation here is f hat here and f hat here. The key property is that this thing, that both of these things are holomorphic. So these projections are holomorphic.
The hat should be the other way around, right?
That's what you mean?
Yeah.
Thanks. So these things have to be holomorphic. So if you look at the standard projections restricted to this thing, they should be holomorphic. I mean, okay, that's nothing. But
you need the graph to be a manifold.
it'll have singularities in it. But you should, right now, since we don't have any experience, you should think of it as a manifold. Okay? So it's
So the two path map of f is just the coordinate map. Is it just the coordinate map?
just the projections. Yes. But if these are just, that's in the case, they're vector spaces or something, but just from one manifold to another. Of course, you're absolutely right, you localize and discuss the matter, writing coordinates. So it's just a projection in coordinate. Okay? It's holomorphic, these are of course holomorphic, but the key thing is that this thing to the left here is a proper mapping. This is very, very important. So this means inverse image of compact sets are compact, and biholomorphic outside a set of at most codimension 2. A set of at most codimension 2. Okay, so you see, if it's biholomorphic, if this thing is biholomorphic here, so this projection here, biholomorphic, it just means that the graph is well defined. It means the function is well defined in the usual sense, right? So except for a small set downstairs, this is really a graph. But there will be a small set where this is not really a graph in the usual sense, and this fiber of this map will be the value. You see, in the set, so the value of this thing, so so if you pull up the point from downstairs, this is of course the image of that point, right? So my 11-year-old granddaughter knows if you take a point up here and bring it over here, that's the image. But if you take a point here and its pre-image is positive dimensional, then its image over here will be positive dimensional. And that's exactly what happens here. The image is all P1. Okay. Now we're going to talk about that more, but this morning Sintal made a really good question. Isn't that something like an essential singularity when you get positive dimensional things? And the point is, if you write down this thing, you look at the video, if you write down this mapping, so F from C to C, okay, Z goes to 1 minus Z squared over this thing. I like that one for some reason. You can write everything down. I mean, the limiting stuff and all of that, all the stuff that goes on, it's horrible, it has singularity, but you will never define it by analytic functions. Okay, you will only define it outside of 0. So outside of 0 it's well defined, right? Outside of 0 it's well defined, it's just the usual graph. You try to define it by and you know what all the limiting values are, it's everything. There's Picard theorem. Maybe it's some, I'm not sure, is some value left out here? Maybe, is it ever 0? Oh, sure.
No, this one takes every value.
No, as you go to 0, it never takes, does this take every value? Okay.
Except for 0.
Okay, so its value set is wonderful, it's P1. And, right?
Except for 0.
Except for 0. Okay, so its value set is even worse.
But 0 is a limit.
Huh?
But 0 is a limit, so if you...
Yeah, I'm asking you, is 0 in the limit somehow?
Yes.
Yeah, probably. I don't know, check it.
Z is real. Go to infinity, it goes to...
No, as you go to 0.
I mean, the fraction goes to infinity when Z is real.
Yeah, I think maybe you're right, but I'm not sure. So,
Yeah, 0 goes to 0 implies...
okay. Anyway, we're talking about the neighborhood of a phenomenon in the neighborhood of essential singularity, and we know all the Picard theorem and all of this. So, it doesn't matter. The value set is something non-trivial, and you will never define the graph by analytic equations. Yeah, it's just horrible. The graph is horrible. And the graph here is not bad at all. And I was going to define the graph here in this case. The graph here, so let F here be from C2 to C, or to P1, and as above. And now, let me find the graph of that thing. The graph of it is the set of points, so I had to tell you, it's the set of points, ZW, now check me on this, ZW, comma, slope, so that effectively I have to do Z over W has to equal, this has to be the homogeneous thing, so I guess it's equal to Z0 over W over Z. Oh, terrible notation. ZW, okay, I'll stay with it, over Z1. And that means that Z times Z1 minus W times Z0 equals 0. Okay, so I wrote down the equation. It's Z, I cheated because I needed scrap paper to do it. And then most people then don't tell you there's scrap paper, but I told it down, I erased it. Okay, there's the graph. Right. That's everything you get, including over 0. So notice we have these mapping on a C2. I called this F upside down or right side up? I think upside down. F check on the C2 and F on the P1. And F check inverse of 0. Well, right, 0, 0. What I put in here is Z equals 0, W equals 0. Right? That's what lies over 0. Z equals 0, W equals 0. This equation degenerates, there's no equation. So that means, to be very precise, it is 0, 0 cross P1. Okay, that's P1. So it's a beautiful quadratic equation. It's a graphic, Mihai doesn't like it.
This is quadratic.
Well, it's degree 2, isn't it? Huh? It's a beautiful, smooth quadratic, and couldn't be more beautiful, right? So, okay. So that's it. And now I want to analyze that thing. Then, on the way. So I want to make a picture of this thing. Because this construction is a fundamental construction of complex analysis. This is called the blow-up of C2 at the origin. The blow-up of C2 at the origin. C2 downstairs, so here's C2, and here are all these lines coming through here. Okay. And the projection, so this is C2.
Isn't it like a Mobius band that you cannot...
It looks much, it is very, your intuition is good. I like your intuition. Let's, so,
you cannot stick it together at the end, that's the thing.
Well, the Mobius band you took together.
Yeah, but it's...
So your intuition is absolutely correct. It's twisting. It is twisting. So here the fiber over 0. So in fact, now I'm going to call this graph the blow-up. So the graph is the blow-up. It's called the blow-up at the origin of C2. And now above this, I don't care whether I'm tall or not, but for giving lectures here, it's useful. So above this is P1. That's P1. That's, let's call this pi now. That's pi inverse of 0. And now what's happening when you blow up in this graph, and you can just check it here in the equation, is you fix this here along a point, say ZW here, ZW. This line up here lifts here into the graph to a line here, which goes into, this is P1 here, goes through the point ZW. You take the line here, which goes through this point ZW, that defines its slope. It goes up here, through the point here, which is in P1, homogeneous coordinates ZW. Now, the reason you see this thing twisting,
Is it the hairball theorem? Like, it does, aren't those the tangent spaces to the sphere?
no, it has nothing to do with that as far as I can tell. I just want you to get a feeling for what this is. What's going on here is if you fix, I hope you see this, this is completely trivial. You fix Z and W, this is a linear equation, it gives you a point, this gives you a line up here. I take another point down here, AB, like that. Well, it goes through AB here, say this is AB. AB, this is line AB. Well, maybe even I'll draw it at an angle, just for the fun. I really don't want to, but I will. Okay? And indeed, if you think about this long enough, what's Mihai's intuition is, I think, correct. You have this P1, and you lift these lines, and as the line goes around the origin, it's twisting around this P1 upstairs. You've seen these artistic things. Artists do this. You have a piece of metal here, a tube, and then they make a surface by twisting lines twisting as you go up the tube. You see it? But if you would blow this tube down, they would all intersect in the point downstairs. Okay, that's what's going on. Okay. And this is an important example because we have the projection. We have the projection of the graph.
So where does the graph live?
Well, I just told you, here it is. It's in C2 cross P1. It's a graph of the meromorphic function.
But it has lower dimension than that thing, no? It has.
It's C2 cross P1 is three-dimensional, and that's one equation. So it's two-dimensional. Okay? Okay? By the way, let's think about this a little more. It's very good to think about this. If I take a point,
So it's like a surface in C2 cross P1.
absolutely. Well, sure. That's the way to say it. Thank you. Here's the equation of the surface. Okay. Now it's a little bit unusual because this is a vector space and this is a projective space. But it's a well-defined equation because these things are degree 1.
Multiplied by constant and
It doesn't change the equation. So it's a well-defined equation. And notice, please, if you take a point outside here, nothing happens. I mean, it's a biholomorphic mapping. The only place that anything happens is over the origin. So really, it's literally blowing up the origin, and everything else stays the same. And that's the reason we say blow up of the origin. Or blow up of a point. You can do this in some general setting. So I just want to look at this just for a second. Let's project this onto P1. Also, that's the second projection. Namely, let me make sure you understand what I'm doing. I take a point, up there, and I map it to the homogeneous coordinate Z0, Z1. Here. Okay.
But they do just the full rotation. They don't come, like, they do just 180 degrees or something.
You mean these artistic people?
No,
Yeah.
no, in this picture they just go 180, they don't go further.
Who's they?
The lines, as they go up P1.
No, they go the whole picture. I understand what you're saying,
And
man. You're
each
saying
point-
that if you
each
think of
point-
this as a rotation, you come back and you get the same line, is what you're
Yeah,
saying.
yeah. So it goes only 180.
So it's only metaphorical. I'm just saying you lift the line and you can think of the line moving upstairs as it moves downstairs.
This is a surface, it's not, I mean, C2 is like R4.
Yeah, I understand.
It's very metaphorical.
Yeah,
But there is, I mean, the point that Mihai is seeing here is, of course, correct. So you're seeing here the sphere. In this case, this is the three-sphere. And you're seeing that these lines intersect the three-sphere in circles. And so that if you would try to do this in some well-defined way by rotation or something, with so many degrees, you have some problems. And by the way, this is the way a lot of times physicists have great problems because the state space is really the space of lines, and yet in quantum mechanics they want to have the space of vectors of norm 1. And so it's taken me a very long time to convince them to go to the projective space and not just look at these norm 1 vectors. And that's what you're doing. You're looking really with close eyes at the vectors. And I'm looking more at the line. But look at this. I take this mapping. What is the fiber of the mapping? So don't forget what the equation is here. The equation is z times z1 minus w times z0 equals 0. Well, you see what that is. That equation for over this fixed point is simply the line z, this line. I mean, of course, it's the line over this point. So to each point, if this is projective space, to each point in projective space we have a line. Clear, right? And you see it here. These are all these lines just in here. It's not so easy. But it's not very hard then to call this vibrational line bundle. So this thing will be now called a holomorphic line bundle. We will, in the very near future, talk about vector bundles and holomorphic phenomena in that way. But this is an example of a holomorphic line bundle of fundamental importance. Very interesting. It looks like this. It looks like this. Here is the P1. So here, this is the line bundle. Here is the P1 above 0. C over 0. And these are all the lines. This is a line bundle over P1. And what you can do in this line bundle is blow down the 0 section. So let's blow down the 0 section, and all of these fibers of this line bundle go through the point that you get by blowing down. So that's called blow down the 0 section of this holomorphic line bundle. So you see, this is a line bundle this way. It is a graph this way which blows down. I've just drawn another picture of it. This is a cone. You see it, it's a cone. It looks like a cone. It is a cone over P1, you see, with the vertex here. However, this cone is smooth, you see, because it's nothing, in this case, this is just C2. So even though something is a cone, a complex cone, it may be smooth. By the way, there's a theorem, this is the only way you can have a smooth cone, is by a simple line and blow up. Okay. So, this even at the beginning, just starting out with some meromorphic function, fooling around and having a good time, we really find some interesting phenomena. In particular, if you haven't had any experience, this is the first holomorphic line bundle you should see. Is blow up a point and the standard projection on a P1 is called holomorphic line. Okay. But let me lecture for another 15-20 minutes.
But it looks like a trivial bundle, isn't it?
No, absolutely not. It's absolutely not trivial, and that's it. By the way, I thank you for saying that this is not trivial. You can ask several questions here. One question is it C infinity trivial? It might be a diffeomorphic to the trivial bundle, or even if it's diffeomorphic to the trivial bundle, maybe it's not holomorphically trivial. This is possible. And in this case, it is neither. Let me tell you what this bundle is. As you see, this bundle is the holomorphic line bundle. So let me just write it again. You blow up the origin in C2, then look at the projections of lines in the holomorphic line bundle. So the fibers are copies of C. So that's a complex line, which are copies of R2. Right, I mean, obviously, so it's an R2. So this is a rank 2 differentiable vector bundle.
Why is it differentiable? Why is it differentiable?
So I need to go into this, which I'm going to go into in the next lectures. But a line bundle, you see, is locally trivial. So that means if you take a small coordinate patch here, this is just the product of C cross this small coordinate patch. And then if you have a change of coordinates, then in the base direction, well, you just have the identity here, but in the fiber direction, it's just changing coordinates. It's a vector bundle, complex vector bundle. It's changing coordinates in GL1, because this is a line, it's a one-dimensional vector space. Okay, well, GL1 is contained, GL1C is contained in GL2R. And so you can just visualize these things as being changed by matrices, which are 2x2 matrices over R on this thing. So just for your own amusement, let me tell you, and for me having a little fun here, let me tell you, you asked about this question, so let me tell you, since you thought about things like this. You can take the dual bundle, so this, let's call this bundle L for a line bundle. And of course, you can replace it by its dual bundle. And that means you just, instead of having the vector space as each fiber, you put in the dual space. Right? We know this. And things that we will do quite often is take tensor products. That means I'm allowed to take tensor product of each fiber with itself. But tensor product of one-dimensional space with a one-dimensional space is one-dimensional. So this is still a line bundle. And this thing, we write this sometimes as L minus 2, we write it like this, because the dual we think it was minus, and the 2. And this is differentiably the same as the tangent bundle of P1 as a differentiable manifold, which is S2. So I had to get to the tangent bundle, which you know is non-trivial, you know. So you can imagine this has to be non-trivial. I dualize and so on. This thing has to be non-trivial. I'm very, very close to the tangent.
No, that was what I was seeing here in this side.
It may be. That may be what you were seeing here. I would love to talk to you about that. So it's very, very...
I don't feel like I have an understanding of this, but it
Yeah,
looks
maybe.
like that it has very much link to S2 not having the trivial tangent bundle.
That's right. This is the link, and this number 2 is involved in the discussion somehow. I don't know about duality, but the number 2 is certainly involved in the discussion. So we're getting ahead of ourselves here, but I mean, it's just something to know, right? I mean, the first line bundle you see in life is the blow up. And then you ask the first question you can ask, how's that related? So is it trivial or non-trivial? What's going on here? What's related? It's very, very close to the tangent bundle. But of course, to get to the tangent bundle, you've forgotten the holomorphic structure. I mean, right, you've forgotten a lot. So in most things, you don't want to forget that much. But, well, it's an interesting discussion. Okay, let me continue. All of this talk is perhaps blah blah because we don't have any examples. So let's return to the one-dimensional case and see what's going on with some examples. And one of the main sources of examples is curves in P2. So let me comment on curves in P2. So, curves in P2. So, with P2C, what is it? It's a set of homogeneous coordinates. It's coordinatized by these linear functions of the standard basis, such that some zi is not 0. So you have some idea. We should look at polynomials. Look at polynomials. So you look at polynomials like some child. So that means you're looking at the polynomial ring with 3 variables. Now the first thing you say about this ring, not just some ring, it's a graded ring. So the gradation is given by homogeneous polynomials. Of degree n. This is a graded ring. Okay? This is much better than just some filtration. This is a graded ring. These are homogeneous polynomials. So then you're in my granddaughter's class and you say, well, here is an example of an equation that comes from this graded ring, namely a linear equation. So from the first interesting gradation. Now you notice that this equation is independent of the dilation. So if you multiply the vector by lambda here, you don't change the equation. So this defines a well-defined, this defines a set, well-defined. So let's say the variety of this, let's call this polynomial just for L. The variety of L, which is just the homogeneous polynomials, I mean the homogeneous things, coordinates, where L vanishes. And L doesn't care what representative you take, it's well defined, right? Okay. You should think of P2 as the follows. You have special ones, special L's. So Z0, Z1, and Z2. Those are generators of the linear thing. So here is Z0 equals 0. It intersects, if you check it, let's say that this is Z1 equals 0. No, maybe this is Z2 equals 0, and this is Z1 equals 0. And for example, they intersect, here is the point 1, 0, 0. And they intersect here, this is the point 0, 1, 0. And they intersect here, this is the point 0, 0, 1. Okay, that's where these things intersect. And this is, of course, this is the variety, if you like, of Z2.
They also they intersect in one point.
Two lines intersecting one point.
No, but
Huh?
they all three have a common point.
They do?
No.
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 Two lines intersecting with it. This is homogeneously. Your point, you take three lines in C3, they all go through the origin, that's what you're saying.
No, I forget that 0, 0, 0 doesn't exist.
That's right, that's right, that's right. So, that's right. Okay. So there exists, just here in projector space, one point. And these things, you will see, even though I have he's dead now, a very good blind friend named Vitushkin, who really sees these things. You see these lines are copies of projector space, P1. You see here, the typical point here is 0, Z1, Z2, and then therefore there's a map to Z1, Z2, which identifies everything, and this thing is a point in P1. So these things are linear copies of P1 embedded in here. And this blind person was able to see these as spheres. Now, I don't know any algebraic geometry who thinks this way. We think of these things as being linear, but he really thinks of these things as being spheres, and it really helped his intuition. He had very deep ideas by thinking about these things as spheres. They are spheres. I mean, they're copies of the Riemann sphere. But they're in there in some linear way defined by a linear equation. Well, okay, here's what's the next thing, Q. Well, let's write something down for fun, I don't care. I'll write everything down. If you want, I can write down every quadratic equation by a quadratic form which is symmetric. So if you go to the degree 2 gradation, level of the gradation, you're dealing with quadratic forms in 3 variables. And what you're interested in, Q equals 0 is where these quadratic forms vanish. So if you think of that as being a line where they vanish, that means the restriction of the quadratic form of the line is 0. So these so-called isotropic lines. But I think of it as a projective space. It's just the points where it vanishes. So this thing, Q equals 0, is called conic. And now that's an interesting thing to start thinking about. There are 3 types of conics. And I will talk about this in the next lectures, but let me just tell you now what the possibilities are. So that's a quadratic form, so the rank of this thing is the only invariant. So really there are only 3 types that can go on, so rank 3, 2, and 1. And rank 0 doesn't occur because that means everything is 0. That's not a valid equation. So if rank is 3 of the quadratic form, this thing really is a copy of P1. It's embedded in there. I will explain. You can see it. I see it very well a certain way. We will talk about that. It's really a copy of P1. Rank 2, it's 2 lines intersecting in one point. And rank 1, it is a double line. So people draw like that. Okay. So it's a quadratic equation which vanishes only along a line with multiplicity 2. And you can see this. What happens is if you take this conic which is non-degenerate and let the quadratic form degenerate, it goes like this. You can imagine the quadratic form degenerating, and in the limit, you have 2 linear equations, right? Product of 2 linear equations. Just let it degenerate. Product of 2 linear equations. And then 2 different linear equations. And then let these 2 different linear equations come together to this product of 2 of the same. That's a double line. So you can think of this dynamically, and you should, that you start with generic conic, which is a copy of P1, degenerating into 2 lines into a double line. This is the beginning of algebraic geometry, But this is easy algebraic geometry, because the next thing to look at, this is degree 2, this was degree, you see, this is degree 2, this is degree 1. Degree 3 is is still understandable. And degree 3, well, the first thing is, if it's not degenerate, it's a torus. And it can degenerate. Of course, one degeneration, you know, looks like this, degenerating, generating, and it generates into 3 lines. But there are other degenerations that are interesting that we can talk about with various singularities. For example, one thing it can do is to degenerate here, and then to something, this whole can come together somehow or another, and this would be a singularity here, an interesting singularity. We can talk about that. Dimension degree 3 is, however, rather easy to understand. And then life gets interesting. Okay? You might ask, you noticed that I had, very easily I found P1 here several ways. That is genus equal to 0. And the next thing that I told you about is a torus, was genus equal to 1. And then you're going to ask me, can I find genus equal to 2 somehow? You might hope. The answer is no. NO. So, a compact Riemann surface of genus 2 is not embeddable in P2. It is only embeddable in P3. So the next genus going up is 3, and so on. So there are gaps in what can be embedded, and we will understand that perfectly. Okay? That we will understand that next time. Oh, just for fun, let me give you a formula. This is a beautiful formula. Look at this formula. Genus equals the degree minus 1 times the degree minus 2 divided by 2. Now, if you don't like this formula, you're crazy. The left-hand side is a purely geometric invariant. The right-hand side is the degree of the polynomial. It's incredible, right? So let me see, degree 2, I hope we get genus 0, right? Right. And degree 3, what do we get here? I hope 1. You're faster. Yeah, 3 is okay, it's 1. Degree 4. So it's quadratic. What do I get here? 4 minus 3. Degree 4. Are you guys faster than I am? 4. 4 here, that's 3 times 2 is 6 is 3. So I skip 2. And the gaps start getting bigger, right? Because it's quadratic. So a lot of surfaces don't fit in P2. Interesting. Then you can ask your question, do they fit topologically? And then you can start asking questions, if something is topologically embeddable, is it holomorphically embedded? Things of that time. Okay. So I think at this point we should stop. Thank you.